Hey, good morning, everybody. I realised that it's been some time since I've provided an update on the Far-UVC research that ourselves and our colleagues have been undertaking. So I thought it was probably a good point to update everybody on the different studies that have been going on and the results from some of our recent experiments as well. Probably the first thing for me to say is that I'm going to be presenting this presentation, which originally I delivered at the British Medical Laser Association meeting, which took place in May 2022 in Edinburgh. And that the work I'm going to be presenting is actually, although it's myself that's presenting it, there were a lot of people, different people involved, a lot of fantastic researchers, and I'll try and credit each of them as we go along, but there's also an acknowledgements slide at the end as well. So the first thing to say is I don't have any disclosures, so no actual or potential conflict of interest in relation to the presentation. And there are collaborators, conflicts of interest, some of them can be found on our most recent publication published in Scientific Reports. This is the structure that I'm going to follow during this presentation. I'm going to give you an introduction to Far-UVC. I know many of you won't need this, but then I'll go on and talk about the work we've been doing around efficacy and around safety of the technology as well. And possibly one of the first things that I want to talk about is the proof that COVID is airborne. And transmission through the air is actually likely to be the dominant transmission route. And there's lots of published articles on this now. A good summary, I've cited a good summary one here, and you can see the link to that in the bottom right hand of the slide. And there's lots of very knowledgeable sort of scientists and advocates on social media who are promoting the fact that COVID is airborne and that we should be putting in place measures in order to mitigate the risk from airborne transmission. Now, you might want to, as well as having good ventilation in your area of practice, you might want to consider things like CO2 sensors, which can be a sort of indication of the number of people in an area that are exhaling CO2 and are a sort of a marker for potential risk. But you might also want to consider some air cleaning technology. And UVC is one type of that air cleaning technology that's available. The UV germicidal effect has been known about for well over 100 years now, since the 1870s. And the UVC photons, well, they've got enough energy that they will damage the DNA or the RNA of the pathogen and prevent it from replicating. It's been used in water treatment since around 1910 and in upper room devices since the 1930s. And it's been successfully shown to be effective at reducing the transmission of measles, tuberculosis, and influenza. The upper room systems are typically from low pressure mercury lamps that emit at 254 nanometers. And at that wavelength, very low doses of UVC can cause problems with the eyes and the skin as well, albeit sort of short-term problems. There's no sort of long-term risk known about or associated with 254 nanometers. But the upper room systems, they fell out of widespread use back in the 1950s. In part, that was due to antibiotics and vaccines becoming available. But there was then renewed interest in the 1980s because of tuberculosis that was resistant to vaccines. So there were various tuberculosis epidemics, and we were starting to see drug-resistant bacteria and hospital-acquired infections as well. Now, the hazards there are hazards from conventional UVC systems, the low pressure mercury lamps, and those are well known, and so it's generally applied to non-occupied spaces. So be that the treatment of water, the treatment of surfaces in an unoccupied room, or indeed in the unoccupied section of the upper part of a room in these upper room germicidal UV systems, and indeed in enclosed units as well. So you see UVC used in a lot of enclosed air filtration units and HVAC systems. The newer technology that we're talking about are these Krypton Chloride lamps. They appear to have the same germicidal efficacy as the mercury lamps in some situations. We'll come on to talk about that. But because of their shorter wavelength at 222 nanometers, they don't penetrate as far into tissue. And because they don't penetrate as far into tissue, they don't appear to cause the same acute or indeed chronic effects in tissue either. The idea, therefore, is that those systems can be used in occupied spaces in order to disinfect the air. And I am going to focus on the air and not on surfaces. And I'll explain why, for me, air really is the target for this technology. Now, I'm going to start by talking about efficacy, and we're going to start on the laboratory studies which have proven efficacy, and there are many of these now, all proving the efficacy of the 222 nanometers. And this is actually a study from Columbia, from David Brenner's research groups. And what it's looked at is the Far-UVC inactivating pathogens in air. And these are probably the best air experiments of this type of setup that I've seen. You can see the setup of the experiment on the left-hand side here. The pathogen of interest is aerosolized and passed through this chamber. And this is the Krypton Chloride lamp. It's actually been turned out for the camera, but normally it's facing towards this chamber. And as the pathogen passes through the chamber, the UV will inactivate it, and it gets collected on the far side here and examined there. And you can see that in these experiments, human coronaviruses had a 3 log reduction at affluence of just 1.7 millijoules per centimeter squared. And actually, the researchers from that group have recently published another paper, and they think that 1.7 millijoules per centimeter squared is probably an overestimate. The actual value is possibly half of what it was. Now, to put that into context, certainly in the EU, the exposure limit is 23 millijoules per centimetre square. So you can see a 3 log reduction, a value which is much less than the current exposure limits. This type of experiment hasn't been done for aerosolized SARS-CoV-2, and of course that's because there's a safety concern around aerosolizing SARS-CoV-2. But SARS-CoV-2 has been shown on surfaces to be inactivated by Far-UVC, so you would expect that it would do the same in air, and actually probably perform better in air than it does on surfaces. And now the reason I say that, and again, the reason at the beginning that I didn't think that this technology, that it'll have its biggest impact on surfaces, is that what makes this technology great in terms of its low penetration into tissue also works against it when there are competing materials around. And by that, I mean, if you have anything in the way that might absorb the UV before it reaches the pathogen, then that's going to reduce the efficacy because this wavelength is so highly absorbed. And in this study, there's a reference at the bottom here. Again, this is not our work. This is the work of another research group. In this study here, you can see that the black bars on the graph on the left are the log reduction at 222 nanometers. And the black bars on the right are the log reduction at 254 nanometers, and that's in a sodium chloride solution. As soon as the researchers introduced any type of artificial sweat or sort of artificial mucosum, you see there's a dramatic reduction in the log reduction that's achieved with the 222 nanometers. So you go from a sort of a 4 to 5 log reduction right down to a 1 to 2 log reduction, something that you don't see the same with in the 254 nanometers. And that's just down to the basic physics. If there's something else there which can absorb the 222 nanometers is not going to reach the pathogen because it is so highly absorbed by most materials. We don't expect this to be a problem in air. And so that's why I said that I think the focus and the real potential for this technology is in the air as well. So moving up from the small scale laboratory studies then, and we start talking about some of our research in a sort of larger scale. So this is the study which we published in Scientific Reports. We undertook the research at a special bioaerosol facility at the University of Leeds in the UK. The picture on the left there is myself and my colleague Kenny Wood. We're inside the chamber doing some measurements of the UV lamps. In the picture in the image, you can see the little purple dots. That's the UV lamps on inside the chamber. The red lights actually come from the plug switches, so you can ignore the red lights. And then on the right-hand side, we have a schematic of the laboratory and what it looks like. It's approximately 4 meters by 3 meters by 2.5 meters high. And the lamps are attached to the ceiling in this room, and they're emitting down into the room, organized in a what's called a quincunx pattern, which is like the 5 spots on a dice. And the chamber itself is mechanically ventilated. It was mechanically ventilated at 3 air changes per hour. And the pathogen of interest, which in this case was Staphylococcus aureus, was continuously released into the room throughout the whole of the experiment. And in the first hour, the room is allowed to build up to a sort of steady state where the pathogens continuously released during that first hour. And then in the second hour, the pathogen is sampled with the lamps being off. And then in the third hour, the pathogen is sampled again, but with the lamps on. And again, emphasizing that all the time, the pathogen's been continuously released into that chamber. It was Wasim Hawar at the University of Leeds who undertook the pathogen experiments, supported by Louise Fletcher, Catherine Noakes, and Emma Tidswell as well. And Wasim's results are shown in this next slide. Again, this is one some of you might be familiar with. What you can read from this was that at the sort of current European or UK exposure limits, we saw a 92% reduction in the pathogen load within the room. So remember, these data is before the lamp switched on, and this the data is after the lamps are switched on. This was with 5 lamps on, and their exposure limited, so it was within the European guidelines. If you look at the new ACGIH guidelines, and this one's for their S prime lambda curve, you can see that there's a 98% reduction, which actually is equivalent to 184 air changes per hour. The 92% reductions is equivalent to 35 air changes per hour. And this would outperform a portable air cleaner, which in this particular space would have delivered 15.5 equivalent air changes per hour. We do expect the system to be even more effective against coronaviruses, and influenza. We haven't managed to get this working yet with our influenza, but we have done with other pathogens, for example, Pseudomonas aeruginosa, and we're seeing values which are equivalent for that. Actually, some of the problems that we have are that the Far-UVC is so effective that it can be difficult to work out to get the resolution of the experiment down low enough to be able to pick out just how effective it's being. These are some new results from the chamber which haven't been published yet. And these represent the lamp as being at the intensity that was equivalent to the ACGIH limits. And what we're doing here is looking at the effect of the 222 nanometers when there's different mechanical ventilation rates in the chamber. So left of the red line is with one lamp on in the chamber. Right of the red line is with 5 lamps on in the chamber. And it goes from 1.5 air changes per hour, 3 air changes per hour, 6 and 9. And again, similarly here, 1.5, 3, 6, and 9. And on the y-axis, there's the percentage that's left compared to before the lamps were switched on. And what you see is probably what you expect, that when you get higher mechanical ventilation rates, the UV becomes relatively, proportionately less effective because, of course, the pathogen's spending less time in the room. And then therefore the particles receive less of a UV dose. But what you are seeing is that still, even at the very high mechanical ventilation rates, particularly if you look at the 9 air changes per hour with 5 lamps, still you see you're getting a really excellent reduction in the pathogen load. There's a median there of still better than 90%, which is excellent. And this is the other results from that study. What we wanted to look at was what happens if you sample the air at different locations within the chamber. And so again, left of the red line is 1 lamp, and right of the red line is with 5 lamps. These are all done at 3 air changes per hour, and either the air inlet is high and the air outlet is low, or it's reversed, so that the air inlet is low and the air outlet is high. And there are 2 sample locations, sample location 1 and sample location 2. So this is just changing different things like the airflow within the chamber, the sample location in the chamber, just to make sure that we still get the same results. And I think what you can see from these is that we are getting the same results. That the 5 lamp experiments, all the data is much more tightly next to each other, which I think just shows you that a nice even spread of UV throughout the chamber means that no matter where you sample, you typically get the same results. Whereas in the 1 lamp, although the median values might be very similar, you get a much larger spread of the data. And that's probably because you're getting a much larger spread of whether or not particles, the type of UV dose that the particles have had, because some will be passing through the single lamp that's in the centre of the room, and some won't be. So hopefully that's a sort of indication about the importance of adequately illuminating the space as well. So we're continuing on with these experiments. We've got a little bit longer to run on our funding, and we are hoping that we can do some, look at some short range inactivation as well in the near future. Now, in terms of larger studies, there is actually only one so far, one published study from the real world, one study that's been published in a peer-reviewed journal, that is, and that was this study by Kitagawa, which came out in 2021. And in this study, they compared two bathrooms, one which was treated with Far-UVC and one which wasn't. The Far-UVC lamps were actually only switched on when there was nobody present. But what you can see here, I think that it's really interesting, is that you see there's a different amount of variation in terms of how effective it is. So there's a significant reduction on the toilet seat, on the control panel of the toilet, and on the toilet paper holder. But you don't see a significant reduction in the door handle or the floor. And that's that's what you'd expect. There will be areas which are shadowed from the lamp where you won't get that effect from the Far-UVC. Also, it's quite interesting that the reduction, you get about a 2/3 reduction in the total colony forming units. So we're not talking about the 6 log reductions that you see inside a laboratory. And again, that will be because in a real world scenario, you can't expect to see these sort of 6 log reductions from this technology. This is a sort of indicating you get roughly about a 2/3 reduction on the surfaces. Actually, what was, and again, that the reason for that will be the same as has already been known for conventional 254 UVC studies, which have been done in hospital rooms, is that oil and grease and dirt and shadowing, all of those things impact the real world efficacy of UVC. Interestingly, the biggest difference between the treated bathroom and the untreated bathroom was seen in this study at 9 o'clock in the morning. And that's because effectively the lamps had the whole night, so several hours to work and deliver the dose to the surfaces. So that was something else worth noting. Real world studies are really difficult to do. We are trying to undertake some, and I'll go on to talk about them at the end of the presentation, but logistically they can be really difficult to get right. And there's a lot of variability in sort of natural microbiology data. So you really need to, they need to be well controlled. Another option then is to sort of try and simulate the environments to simulate what the inactivation of the pathogen might look like. And that's what we're doing. This is the work of Kenny Wood and Camilo Pereira and Andrew Wood, who've been looking at using computational fluid dynamics and Monte Carlo radiative transfer to simulate the Leeds, the University of Leeds bioaerosol chamber. And you can see on the left-hand side of the picture here, this is the particles as they are traveling around the room. Particles in yellow are sort of fully active particles, and particles in blue have been completely inactivated. So you can see how those particles move around the chamber and how as they move around, they become, they move from yellow to blue as they're being inactivated. And then the graph on the right here, what we're doing is comparing the computer simulation results to the results from inside, the experimental results from inside the chamber, basically to validate the model so that we can on and use that model to explore larger spaces and have some confidence that the model is actually producing accurate results. And we're getting good agreement. I think you can see quite clearly from these graphs that there is a really good agreement, which does validate the model. And it means that when we're looking at larger environments, for example, in this classroom at the University of St Andrews, we simulated this in a publication which was published in the journal Photochemistry and Photobiology, and the link's at the bottom of the slide. You'll see that, well, you can see the detailed results of that in the publication, but the take-home messages were that you get improved efficacy from the Far-UVC lamps if you increase the lamp intensity, and that makes sense. You get improved efficacy if you ensure that there's a good spread of UV throughout the room. So having more lamps improved the efficacy than having just a few lamps. And also in our simulations, it was important the lamps were on continuously and not on a duty cycle, because in the periods of the duty cycle when the lamps were off, the pathogen could spread around the room and infect people. So modelling is also useful because it allows us to look at other aspects that are difficult to do experimentally. So, for example, to look at short range inactivation. I did say we are going to try this in the bioaerosol chamber. We suspect that it might be quite difficult to do. But if we look at the simulation from the computer models, and we take a snapshot at a height of 1.5 meters inside the chamber, and we look at the pathogen concentrations that are in the room when the lamps are on, which is what's on the left. And again, the scale is yellow to blue, for yellow is active and blue is inactive. And when the lamps are on, which is the image on the right here. So you can see in the images that there's more blue when the lights are on, so that there's more inactive particles around when the lights are on. And if the yellow star is our source location, so you imagine this is somebody breathing out some type of pathogen here, depending where you are stood around them, you could get up to sort of 95% less pathogen within just 1 meter of that source. So that's what the short range inactivation is suggesting from the modelling. And really we're seeing now a sort of significant growing body of evidence around Far-UVC inactivation in laboratory settings, but I think we really need those real-world studies, which they are being undertaken at the moment. You know, they are coming, but they will be very, very important to determine whether or not this technology actually does work and how well it works when we're in a sort of real-world situation. That's efficacy that we've gone through now. So I think maybe if we move on to safety next, and the first thing we need to look at is this indication that Far-UVC penetrates less far in tissue. So we know the UVC photons at 222 nanometers have enough energy to damage DNA in cells. So that's just the basic physics. As the wavelength gets shorter, the energy of the photon gets higher. And we know that those photons, when they're incident on the surface, that they are highly absorbed at the tissue surface. So they're highly absorbed in the stratum corneum, and they don't penetrate very far into the tissue. So in the slide that you see here, the image on the left is a computer model of the skin. It's a 5-layer skin model. On the x-axis, we have the wavelength in nanometers, and on the y-axis, we have the depth into the skin. So the top of the image is the skin surface, and then this is a log scale. And it's presented on a log scale so that we can see the stratum corneum nicely, because of such the high absorption in that stratum corneum. In reality, of course, the stratum corneum is very, very thin and not as thick as this. And as you can see on the image, there's different coloured lines to represent the percentage of light that reaches a particular depth. So if we go round about the 222 nanometers, less than sort of 0.1% of that actually gets beyond the stratum corneum. The longer wavelengths will penetrate further. So it is important in order to filter the Krypton Chloride lamps in order to remove those longer wavelengths. And there's this is not just modelling evidence which indicates this, there's also good experimental evidence as well to support this. This is a publication by Louise Finlayson, who's a PhD student at the University of St Andrews, working with Kenny Wood and myself, and it builds on previous work from Isla Bernard in this area as well. And there's the line indicating the 222 nanometer point. So you can see that just less than 0.1% actually makes it beyond stratum corneum. So if we look at the physical evidence of this, the first human study was actually done in the photobiology unit here in Dundee at Ninewells Hospital. That was done back in 2014, and in that study, skin redness was seen at relatively a low exposure. So you're getting a minimal erythema dose at around 40 to 50 millijoules per centimetre squared in these subjects. These were subjects who had a Fitzpatrick skin type 1 to 2, which means they are some of the more sensitive to UV. It's fairly typical of a Scottish population. And in those individuals, we also saw that there was some CPD damage seen in the basal layer. Now that was, looking back on it, unexpected, but it's important to note that that was with an unfiltered Krypton Chloride lamp. When the longer wavelengths from those lamps are removed, we don't actually see any acute effects in the skin until you get to really incredibly large exposures. And we published on this, it was 6,000 millijoules per centimetre squared before we saw any visible changes in the skin of a single individual, and which is hundreds of times the actual exposure limit. And if we look not just at the visual response of the skin, but if we do some histology, so if we take a punch biopsy and we look at the CPD, the cyclobutane pyrimidine dimers, which are just a type of DNA damage. If we look at that type of DNA damage, we see that it occurs just below the stratum corneum. So you can see the darker brown spots highlighted in this image. It's important that these are at the top of the epidermis, because the cells at the top of the epidermis, well, they can't replicate, so they can't pass on that DNA damage to other cells, and ultimately they're on their way up into the stratum corneum, and then from the stratum corneum they'll be sloughed off of the skin. That's the process through which the skin cells are generated in around this basal layer marked with the dotted line, and they move their way up and through the skin as they age. You can see there's two publications from our work related to this. One, both published in 2021. One's Edie et al., and the link again at the bottom of the slide, and Hickerson et al., and the link again at the bottom of the slide as well. In order to put this kind of into a bit of perspective, we have to sort of compare, we maybe compare sort of Far-UVC to what it's like if you get sun exposure, because that's where we're used to getting our DNA damage on the skin from, is from the sun. And what you can see is that with a filtered Far-UVC source, really you need to spend hundreds to tens of thousands of hours in order to get the same number of CPDs that you would get from just 10 minutes of English summer sun. And that's English summer sun, so that's not even talking about sort of Mediterranean summer sun. And that's because the longer wavelengths of the sun do penetrate further into the tissue and can get down to that basal layer. Again, the data from this is in another publication from 2021, and the link again is at the bottom of the slide as well. Now, I think we've probably got enough in vivo human data now to demonstrate that there are no acute effects from filtered Krypton chloride lamps. I haven't gone through evidence from other groups, but there is evidence from other groups. There's a small trial that was carried out in humans as well. So what about the sort of chronic effects then? So if this is intended to be used day in, day out, irradiating the space that people are moving in regularly, what kind of chronic effects can we expect? Well, we can't spend our time irradiating a controlled group of humans for the next 50 years in order to see what's going to happen. So the next best thing that we have to look at is mice, and there's been 2 studies on that. Again, this is not our work. So this first study was from Japan. It is industry sponsored, and in this study, the mice received weekly 10 weeks of exposure with 100 millijoules per centimeter squared twice per week. And then they followed up for a further 15 weeks after those 10 weeks of irradiation. And these were in mice who are susceptible to the type of DNA damage that causes skin cancers. And what you can see from the graph on the right here is that the mice, the triangles who were exposed to a broadband UVB source, so they started to develop skin tumors from week sort of 13, 14 onwards. But the mice who were exposed to the 222 nanometers, they didn't have any skin tumors at all. Nothing was seen there. So that study was for sort of 25 weeks. There was another study from Columbia University where they looked at 96 mice with a 50-50 split between male and female. And they split those mice into 4 groups of 12. So they had a control group who weren't irradiated. They had a group who were irradiated with 50 millijoules per centimeter squared every day. Another group where it was 125 millijoules per centimeter squared, and a 4th group that were 400 millijoules per centimeter squared. And they had 66 weeks of exposure, 8 hours a day, 5 days a week. So you can think of this as like a working week. And when they looked at the results from these mice, they saw that there was no difference in weight across any of the groups. There was no difference in mortality of the mice across any of the groups, and that there was no skin cancer seen at all in any of the groups, and no difference between the groups with regards to non-cancerous skin abnormalities either. So really no difference at all between the control group and the different Far-UVC exposures, which is very encouraging. All of those results relate to the skin. And what I would say is that they come with a bit of a caveat, and that almost all of the safety work thus far has been done with highly filtered Krypton Chloride lamps. Most of it, in fact, all of it in the humans with Ushio lamps, which have the sort of best filtration of all the lamps that I've measured thus far. So most of that data relates to those particular lamps. So it's not to say that those results are necessarily replicated across the board. And there's been less evidence and less research done on the eye. Again, there has been a couple of studies from Japan, both industry sponsored, and the initial study showed that there was no corneal damage in these Sprague Dolly rats at doses up to 600 millijoules per centimeter squared. And then that was followed up by another study from the same group, which demonstrated at the 222 nanometer wavelength that CPDs are only present in the most outer layer of the corneal epithelium. And in fact, they worked out a threshold radiant exposure for damage to the eye with 222 nanometers, somewhere between 3,500 millijoules per centimeter square and 5,000 millijoules per centimeter squared. There has been one clinical study undertaken in humans that I'm aware of. It was undertaken in Japan, and I believe that the study is complete, but will report within the next few months. There are other kind of safety concerns, questions that people have about how UV might interact with chemicals in the environment, or about creating sort of too sterile an environment. And there's lots of reasons to debate around that topic. We can do thought experiments to work out what we think will happen. But there's really been very little in terms of actual experimentation and published experiments done in that area. And it's all a little bit beyond the sort of time limits that we've got for this presentation. So just to conclude then, I think what we see from our large laboratory studies is that there isn't any other technology that we know of that can produce the same sort of high equivalent air changes that the 222 nanometers can. None of the sort of newer technologies that you've seen around sort of air cleaning and internal air quality has the same published evidence base that 222 nanometers has. And I'm talking about the sort of newer technologies, not the HEPA filters, which have been around for a very long time. So there is a good and a growing evidence base for 222 nanometers. Much of that evidence base is industry sponsored. We try to keep ourselves independent, and we'll certainly always be as transparent as we can in terms of noting all of our conflicts of interest in all of our publications. But we could definitely do with more research in this area, particularly research, as I said, is a sort of real world. How does it actually work in the real world? And those studies are going on just now, and hopefully we'll hear more from them soon. All the evidence at the moment is pointing towards minimal risk from the 222 nanometer wavelengths. Again, that's with the caveat that almost all those studies have only been done with one type of lamp, which has a high degree of filtering. They've also all primarily looked at CPDs, cyclobutane pyrimidine dimers, although there was a laboratory study published recently which actually suggested that maybe double strand breaks to the DNA are more prominent with 222 nanometers, and so we should try to look for the double strand breaks rather than the CPDs, and that's something that we are doing, and I'll come on to talk about that in the next slide. But I think so it does appear as if there's minimal risk from 222. Whenever we're talking about risk, we always need to weigh it against the risk of not doing anything. And you know, in some situations, there's a really high risk of not doing anything. Coronavirus numbers are higher in the UK now than they have ever been, and we don't yet know what the long-term effect of having coronavirus or multiple bouts of coronavirus will do to our population. So there's still lots of scope for more research, and we're certainly trying to do our best to do that. So at the moment we've got a clinical study which is looking at the effects of the Krypton Chloride lamps in the skin, and you can find out more details at the link on the screen there. The study's in 2 stages. The first stage has now completed, and we had 8 volunteers, and we looked at high single exposures. We went up to 3,000 millijoules per centimeter squared, and we observed the skin visually every hour for 8 hours. And we also took biopsies to look at the histology, and we're looking at a range of different markers in the histology, not just the cyclobutane pyrimidine dimers. In stage 2, which we've just started in the last week, we are irradiating individuals twice a day for 4 days before we then take a biopsy and look at the histology. And the idea behind that is to try and look at what happens when there's a more regular, rather than just a one-off irradiation, a more regular irradiation on the skin. We're also partway through a study looking at eye discomfort in a sort of typical office deployment of Krypton Chloride lamps. The volunteers to that study attend for 3 days, and they experience a sort of randomized order of either no exposure, standard exposure, which is equivalent to the 23 millijoules per centimetre squared if you were stood directly under the lamp, and a high exposure, which is equivalent to about 10 times that value. The volunteers then complete a sort of series of standardized questionnaires, which will tell us about any eye discomfort that they may have. And the idea behind that is to in a controlled manner investigate whether or not there's likely to be any eye discomfort when the technology is deployed in different ways. We are continuing our studies in the bioaerosol chamber. I've presented some of those results here, but we're also looking at testing other pathogens and hopefully some short-range inactivation experiments as well. And then as part of a Scottish business research initiative that is called Harsane, Krypton Chloride lamps have been deployed in a toilet at Ninewells Hospital in Dundee, and we're undertaking a series of air and surface sampling in a randomised double-blind study design, where both the people taking the samples and the analysers of the samples are unaware of the irradiation schedule that the lamps were in. So that's some of a bit of a brief run through of our research. There's a lot more research on 222 nanometers out there. There's a lot more has appeared in the past few years. It's too much now to fit into a single presentation as I might have done in the past. But I hope you found that interesting and that it's encouraged you maybe to get involved in some future research in this area. I tried to mention everybody during the presentation, but I'm sure I've probably missed people. There's been lots of people involved in this, lots of researchers, lots of students, our colleagues from various universities, both in the UK and further abroad. I just want to say thank you to all of them for all of their discussions and everything that they've been involved in. I also want to acknowledge the funding that we've received and the different funding bodies who have believed in the work that we're doing. And also to thank the various manufacturers who have lent us equipment and thank them for their willingness in order to support that independent research in a time of human need. It's been absolutely invaluable, and all of the companies have loaned us equipment without any influence on the research that we perform and without any interference in the results of that evidence as well. So thank you very much for listening. I hope that's been of interest to you, and I look forward to seeing everyone soon. Thank you. Bye.